Hey, I'm Jan van den Brandt, and I want to talk about bipartite matching in nearly linear time on moderately dense graphs. And this is joint work with Yintat Li, Danupon Nanongkai, Richard Peng, Thatchaphol Saranurak, Aaron Sidford, Zhao Song, and Wang. And while the title here is bipartite matching, what we're actually solving is a more general class of graph problems. What we're solving is transshipment. You can also refer to this as minimum cost flow without capacities. So it's min cost flow, but on any edge, there is no upper bound on how much flow there could be. In this graph problem, you're given a directed graph, and every edge has assigned some cost, and every vertex is assigned some demand. So how much flow does it want to send or receive? Now what we want to do is we want to find a flow that minimizes the cost, and this flow needs to satisfy the demands that we have for the vertices. Here this A, this matrix, is just the edge vertex incidence matrix, so this really just means the demands need to be satisfied. And this constraint here, that F needs to be non-negative, just means that since we have a directed graph, what we want is that the flow actually is aligned with these directions. It doesn't go in the opposite direction. All right. And this transshipment problem is quite general, so it captures a lot of other graph theoretic problems such as maximum cardinality matching or minimum weight perfect B matching, both on bipartite graphs. But it also captures negative weight shortest paths, optimal transport, and vertex capacitated min cost flow. So we have an algorithm for all of these graph problems. For the history overview, I want to focus on the maximum cardinality matching here. This is for bipartite graphs. And if we look at the history and we assume we solve matching on a dense graph with a lot of edges, then the fastest algorithm was here in matrix multiplication time. On the other hand, if we assume the graph is really sparse, then there was a sequence of works where they managed to solve maximum cardinality matching in m to the some exponent. The exponent decreased over time, and the current best bound is m to the 4/3. And since the exponent decreased over time, it kind of raises the question, is nearly linear time possible? Could the exponent be decreased all the way down to 1? And we show that yes, that is possible if you assume that the graph has at least n to the 1.5 many edges. So we have an upper bound that says you can solve transshipment, maximum cardinality matching, and all of these graph problems that I listed before. You can solve them in m plus n to the 1.5 time, hiding polylog factors. All right, so how does this algorithm work? So the high-level idea of this algorithm is that since transshipment has this nice LP formulation, we're going to use an interior point method, which is typically used for solving linear programs. For those here that do not have a background in optimization, you can think of an interior point method as some kind of reduction. In this case, we are reducing transshipment, bipartite matching, and so on. We're reducing that to the task of just computing a bunch of electrical flows. And electrical flows, it's known that you can compute them in nearly linear time. That's a result by Spielmann and Teng. And that means the complexity is kind of bounded by how many electrical flows you need to compute. And if we look at the history, then the number of flows we need to compute reduced over time. The best upper bounds are by Li and Sidford that said you need root n. So here n is the number of vertices. You need that many flows. Alternatively, Kathuria, Liu, and Sidford show that you can also do it in m, so the number of edges to the 1/3 many flows. And that then, using this algorithm for computing electric flows, gives these upper bounds. So while the history, like the past research, was about reducing the number of flows you have to compute, our new idea now is instead to reduce the time we need per flow. So our algorithm will need root n many flows, like this result by Li and Sidford, but we reduce the time that is spent to compute the flow. So we are going to beat this nearly linear time per flow. So for that, I first want to give some intuition on what exactly does the interior point method do. So if we simplify a bit, then you can think of the interior point method as the following type of algorithm. Remember, we want to solve transshipment, which is like minimum cost flow, but we don't have an upper bound on how much flow there is on any edge. There are no capacities. So let's assume we already have a flow that satisfies our demand vector D, but it's not the min cost flow, right? The cost is not optimal yet. Let's say the black edges here are our flow, and these edges have, like, let's say, a really large cost. Maybe the cost up here is a bit less. So what we could do to improve this flow is to augment it by this circulation, these yellow edges. So we just take away some flow on these edges and reroute it by flowing along the top. So just repeated augmentation by a circulation to reduce the cost. That's kind of what the interior point method does. How this is constructed, why this has a connection to electric flows, is that you typically try to first reduce the cost. Right? You have some flow G that reduces the cost, but if you augment by this G, then the vertex demands here are no longer satisfied because you have taken away some of the flow. So you need to fix this error in demand that you have. And that is done by this green part. So we have another flow that goes now from the left to the right that fixes the demand. This flow is computed as an electric flow, and the resistances on this graph are chosen in such a way that it doesn't increase the cost too much. And you also don't get like a flow that goes in the opposite direction than the direction of the edge is pointing. All right, so you kind of have two augmentations, one to reduce the cost and one to fix the demand. And if you do both of these augmentations, you then satisfy the demands again, and you have reduced the cost. Then you just repeat this over and over again until you get really close to like the optimal solution. So you can just round to like the nearest integer and say that's the optimal solution for this min cost flow, this transshipment instance. Okay, now how can we speed this up? Our idea is to say, instead of saying this initial flow F that we have satisfies the demand exactly, we say it satisfies the demand approximately with respect to some norm. Right, so we say this is the demand of our flow, and the distance to D is just going to be kind of small. Now, if we reduce the cost by augmenting by G, it might be that the new demand is like not even close to the desired demand of D. It could be that this norm is going to be really large. So what we want to do is we want to fix this error in demand, again by computing some electric flow here, this green part. But since we don't want to completely eliminate this error, we just want to reduce it, this electric flow doesn't have to be exactly this D minus the actual demand that we have. Right? It's enough if this electric flow is just roughly satisfying this demand here, because we just want to reduce the error. We don't want to completely eliminate it. So what this means is our electric flow doesn't have to be computed exactly. We are allowed to perform some approximations to speed things up. So the summary here is interior point method. That's kind of a reduction that reduces transshipment, shortest path, bipartite matching, and so on to a sequence of electric flows. Previous research focused on how to reduce the number of flows that you have to compute. And now our idea is to reduce the time you need to spend for computing one of these flows by computing the flow only approximately. Okay, so then the next part is, how can we compute these approximate electrical flows efficiently? How can we do this really quickly? So let's first look at electric flows. How do you usually compute them? Let's say we have a weighted graph G and some demand vector B. Typically, if you now want to compute the electric flow, what you do is you take the weighted Laplacian and solve this Laplacian system here. So this phi here is the unknown that we want to solve for, and this phi is also called a vertex potential. So every vertex receives some potential, and now if you want to compute the flow, you just take the difference of these potentials and scale it by the weight of your graph, the weight of that edge. Okay, so how much time do you typically need for this? It's known that solving a Laplacian system can be done in nearly linear time by Spielmann and Peng. And then for every edge, we need to compute this difference and scale it. That's also linear time. So that's why computing an electric flow typically needs nearly linear time, because you can compute it this way. So how can we speed this up? The first thing is we don't need to satisfy the demand exactly. So it's enough to just replace the Laplacian that we use in this linear system. We can replace it by a spectral sparsifier. That's kind of an approximation of the original Laplacian, but this new approximation is much sparser. And if you run the Laplacian solver on this sparse variant, the time is only going to be linear in the number of vertices instead of the number of edges as over here. So that's the first speed up. The second part is we would have to compute the difference for every edge. That's going to take a lot of time. Let's sample a random set of edges of size, let's say m over root n, and we only compute the flow on this subset, right? So we don't compute the entire flow, we just sparsify the flow here. All right, and the idea is if we do both of them, then we can get this m plus n to the 1.5 bound that we had. The idea is you need root n electric flows. That's by Sidford from 2014. If you need that many electric flows, and every time you need to solve the system in nearly linear time, then you get this n to the 1.5 term. Additionally, if you always compute the flow on m over root n many edges, you need to repeat this root n times, then you get this m term here. So that's where our complexity comes from. Okay, so how do we perform the sparsification? So let's say f is the actual electric flow that we would compute if we do things exactly. What we want to do instead is we sample every edge with some probability PE, and just scale. If the edge is included, then we just scale the flow by the inverse. Otherwise, the flow is zero because we want to sparsify it. If we do this, then in expectation, this new sparse flow is still the same as the original flow. But how should we choose the sampling probability P? So we need two properties. The first thing is, while the flow is still the same in expectation, it doesn't actually have to be close to the flow, right? But we want that this new sparse flow is still rather close, and it should be an approximation of the original flow that we had. So what we want to do is we want to sample every edge proportional to how large the flow is on that edge. It's going to be proportional to the flow size squared. This down here is just a normalization, and remember I said we want to have m over root n many edges, so that's just the scaling here for the probability. And if we sample by some probability that's lower bounded by this, then the variance is going to be really small. Okay, so that makes sure the flow is still roughly the same as the non-sampled variant. Additionally, right, we want that it approximately satisfies this demand B here. So what we do for that is we also want that the sampling probability is at least the effective resistance of the respective edge, because we know that if you sample by the effective resistance or some probability that's larger than that, and you scale by the inverse of the probability, then with high probability you get a spectral sparsifier, which means if we just compute the demand here of our sparsified flow, what we're really computing is the vertex potentials times a spectral sparsifier, where the sparsifier is given by which of the edges we have sampled for our flow. And since this is a spectral sparsifier, so it's like an approximation of the original Laplacian, and phi is exactly the vector that satisfies this equality here, or not exactly, but approximately, because we used another spectral sparsifier, we have that this is roughly our demand vector B. All right, so these are the two properties we need for the sampling. In summary, what we now know is, okay, we can reduce the time that we need to spend per electric flow by just using the Laplacian solver on a spectral sparsifier instead of the entire Laplacian. Additionally, when we compute the flow, we don't compute the flow on all of the edges. We only compute the flow on a small subset where we sample the edges by some probability that's lower bounded by this term here. So at least something that depends on the size of the flow, plus the effective resistance. Now, this kind of raises a new question, and that is, the point of sampling is that we do not want to compute the flow for every edge. But how can we perform the sampling if it depends on the flow? Kind of implies that we would need the flow in order to perform the sampling, right? So how can we perform the sampling without computing the entire flow? So what we do is we create a new data structure. So this data structure receives some weighted graph as input. It's allowed to perform some preprocessing, and over time the edge weights might change a bit. And the hard part here is the query operation, where we are given the vertex potentials and some scaling S. And now we want that every edge UV is sampled with some probability at least proportional to the flow on that edge squared, and it should also be lower bounded by the effective resistance of that edge. And typically how we do this is that we have 3 steps. So first we sample proportional to the flow, then we sample based on the effective resistance, and then we just take the union. Then we get this property that it's at least the sum of the two. Okay, and I want to start with the easier case for how to sample based on the effective resistance. That is known already. I just want to repeat it because we are going to use some of the techniques. So let's assume that this graph that we are given is an unweighted expander. I'm going to remove this assumption later. If we have such an expander, let's say the expansion is at least k, then we know the effective resistance is at least 1 over the degree of the 2 endpoints of that edge, and some factor that depends on the expansion. And this is useful because now we can perform our sampling by iterating over the number of nodes. We fix some probability that for every node is just 1 over the degree, and this factor that depends on the expansion here. And now we just perform a coin flip for every of the incident edges. The nice thing is that these coin flips, like this binomial distributed variable, can be generated efficiently so that the time is just proportional to how large this x is. And then you just pick a bunch of incident edges uniformly at random. The point here is that if you do this, that's equivalent to sampling every edge with probability at least the coin flips of the 2 endpoints. And well, maximum of these 2 probabilities, right? If we look at that's the probability here, that's exactly the upper bound we had on the effective resistances. So this sampling scheme does sample every edge with probability at least the effective resistance. Every edge is sampled independently. And the nice thing is this is quick because we just iterate over the number of vertices, and for every vertex we have roughly 1 over k squared many edges that are going to be included. So the time we are going to spend is just nearly linear in the number of vertices, assuming the expansion is high enough. All right, and now we want to modify this, so we can also use this for sampling the edges proportional to the flow. So we assume again everything is an expander, and we just want to sample proportional to this flow squared. As a reminder, since we assume it's an unweighted graph, the flow is just the difference of the vertex potentials, and then we square it because we want to sample based on the flow squared. All right. Since we take the difference of the vertex potentials, we can just shift all of these potential vectors by just the all ones vector in such a way that it becomes orthogonal to the degree vector. And then we can do the following. I'm going to explain this algorithm first, then I explain why it works. We iterate over the number of vertices. We again fix some probability for like coin flips, and we again perform a coin flip for every edge that's incident to that vertex. Again, implementing this binomial distributed variable can be done more efficiently than actually iterating over the incident edges. All right. Why does this work? So this sampling scheme means we just sample every edge at least with probability of the maximum of the 2 endpoints, right? These 2 coin flip probabilities of the endpoints. Now we can use the Cheeger inequality as follows. Cheeger inequality says if these vertex potentials satisfy this orthogonality assumption, then the norm of our flow is lower bounded by this term. And that we can use, because now the maximum of these two sampling probabilities is just, well, the maximum of the squared vertex potentials with all of this normalization that we have from here. And now we know that this term down here is exactly the lower bound of the norm of our flow. So we can replace the denominator here by the L2 norm of our flow. Additionally, the flow here, right, is just the difference of two vertex potentials squared. So this flow is also smaller than the maximum of these two vertex potentials. So overall, this probability here is definitely an upper bound on that term. So we sample with some probability that is at least this term here. All right. Now, why is this efficient? Well, we iterate again over the number of vertices. Implementing this binomial distribution can be done efficiently so that the time is just proportional to what the size of x is. And then you just need, well, for every vertex you pick, degree times this coin flip probability. But thanks to this normalization, right, if you take the sum here over all of the vertices, this is just going to cancel with the denominator. So overall, how many edges do you have? It's just the scaling s that we use divided by this k squared that we have over there, which is the expansion. And when it comes to measuring the time, we also need to remember that we shift this potential vector by the all ones vector. So we also spend n time. Okay. And as a reminder, s is going to be something like m divided by root n. So this is going to be faster than nearly linear time in the number of edges. Faster than the number of edges. All right. So that is how we do it on expanders. Now, how can we generalize it to general graphs? And for that, we use a dynamic expander decomposition. That's just the data structure that receives this graph with these changing edge weights, and it just decomposes everything into a bunch of expanders, where every expander has a quite high expansion. And then we just run the sampling scheme on each of these smaller subgraphs, which are an expander. So, in summary, we kind of have two new ideas that this algorithm is built on. The first is a new interior point method, which is using approximate electric flows. And interestingly, this can be extended to general linear programs that don't have this graph structure for some other type of approximate augmentations. And now that we know that these approximate electric flows suffice, we can use this to reduce the time per flow, which also is then going to reduce the total time of the algorithm, obviously. And this reduction in time comes from using spectral sparsified Laplacians and sparsifying the resulting electric flow. These sparsifications are done via some new data structure, which is built on top of the dynamic expander decomposition. Okay. Now, what are the open problems that kind of came up while working on this? So the exact complexity of our algorithm is m plus n to the 1.5 times log square of w. Here w is the upper bound on the largest demand that you have in the transshipment instance, or the largest cost on any of these edges. And we claimed that this is nearly linear time on moderately dense graphs, which means, well, at least n to the 1.5 edges must be in the graph. And that's kind of one of the bottlenecks here. So it would be interesting to see, can this n to the 1.5 term be reduced? Can the exponent 1.5 be reduced to a smaller number? And yeah, that would be really interesting to see what techniques are required for this. All right, thanks for listening, and I will see you at Fox.